Waalaikumsalam, sir.
Okay. So we have this formula here to calculate normal stress. Right. Okay, just a simple formula here to calculate normal stress. Yeah, we call these normal stress. Okay, yeah, because the internal loadings, the internal force is normal internal force. P here is the normal internal force. Right, yeah, divided by area. Okay, so let's say this is the bar. Okay, it's loaded with P. It's loaded with this force P. All right. So this is the external force. Yeah, this is the external force. Okay. This is external force. External. Okay, external force. Okay, not this value that we input it here. No. Right. What we need to input it here is the internal force. Force in the material. Okay, normal internal force. Yeah, normal internal force. All right. Yeah, so we have done internal loadings, right? Yeah. Okay. So to calculate the normal stress on this section, on this area here, right? We need the normal internal force. In this case, is equal to P lah. Right. Nah, this is internal force. Yeah. This is internal. All right. The one that we input it in the formula is the internal force here. Right. Yeah. The result of the total lah. Yeah. Is okay. What is the internal force acting on this point here is not our level to calculate. All right. It's advanced level. Right. But we know that for equilibrium, if we total up all those internal forces, it must be equal to P, right? It must be equal to this P, right? For equilibrium. Right. Yeah. For each point, not our level to determine. All right, is advanced level. Okay. Yeah. And for our level, we assume that the internal force is uniformly distributed, okay, on that section here, on that cross section. Okay, yeah, on this cross section, yeah, is uniformly means that each of the internal force is equal value lah. Okay, yeah, we assume is to be uniformly distributed, okay, on this area. Yeah. Right, that's our level lah, yeah. Okay. Right. Okay. So that's a simple formula, right? It's just a simple formula. Okay. Yeah. So the challenge is to find the internal force. Yeah. That's the challenge. So we need knowledge of statics here. Right. Yeah. The structure can be this. Okay. Or can be this. Right. Yeah. That's the challenge lah. Right, to find the forces, yeah, the internal force, to input it in this formula. Right, divided by area, the cross-sectional area. Right, it can be any shape lah. Yeah? So use the formula that you learned during your mathematics class, to find area. Okay, yeah? If the circular, then use formula to calculate area for circle. If this square, use the formula to calculate area for square. It can be any shape. Right, shown here, right? Okay, shown here can be any shape lah, as long as you know the area, how to get the area, right? Okay, so you get the normal stress. Okay, the SI units for force is Newton, right? Okay, and the SI units for area is meter square, right? So the unit for normal stress is Newton per meter square. Okay, or Pascal, yeah? PA, right? Pascal. Okay, it's the same unit as pressure, but it is not pressure.
Sir?
Yes.
Sorry for interrupting, but can you please add the people that is waiting for you?
for Google Meet.
Okay. Right. Okay, so normally for metal, the force that can be applied to metal bar, bar made of metal, made of steel, made of aluminum, it can carry high load. Yeah, it can carry high load, high force. Okay, and over a small area. Over small area. So normally the value of normal stress, normal stress is sigma. Yeah, the symbol is sigma. So use the correct symbol. Right, for normal stress, sigma. Right, okay. So normally, the units for stress can goes up to 10 power of 6, right? But not every time lah. Depends on the load lah. Depends on the applied force, All right, but normally can goes up to megapascal, megapascal times 10 to the power 6. Sometimes megapascal, sometimes kilopascal. Depends lah, on the applied load, applied force. Okay. Right, and also, all right, our level, okay, we assume that the internal force is uniformly distributed. Okay, over the cross section. This is okay if the section is far from the applied force. If you make section somewhere near here, let's say, okay, if you make section somewhere near to the application of the force, the external force, right? So if I sketch this section near, when you make section near to the applied force, in reality, right? In real life, the internal loading is not uniformly distributed. So maybe it's higher at the center and small at the edge here. Right. So I represent the value by the length of this arrow lah. Right. So the internal force, this is especially when you make section near, to the application of the force. Okay. Right. Okay, so when you make section near to the application of the force, the internal load is not uniformly distributed, but the total must be equal to P lah. Right, so the value here somewhere here a bit higher. Okay, at the center is higher, right? Okay, but if you added all those internal force, it must be equal to P lah. It must be equal to P, right? So if this on the internal force on this area here, on this point here, you get stress value, right, which is less value as the stress at the center, right? Stress, force over area, internal force divided by area, small area here lah, right? And the internal force divided by the small area over here, right? You get different value of stress. But if you take the average, it's the same as this, the same as the average. So that's why we call it average here. Okay, that's why we say average here, average normal stress. Right. If you take the average stress, okay, it's the same as if you take the average, you get sigma equal P, same thing, same value lah. Right. So means that when we make section our level, we don't make section exactly at the point where you apply the force. We don't make exactly section here. No. Okay, the internal force is not uniformly distributed. We make section far from the application of the force, or it can be a support also lah. Like this, right? Okay, like this. Okay, we make section at the A and B. We don't make section exactly at B because the force is not uniformly. We make section between A and B. Okay, in between, All right. And we make section. We want to find the normal stress in BC. we make section far from the application of force. It somewhere here, like at the center here, right? Yeah, CD. So here we have support here. We have reaction here, right? So same thing. We don't make section exactly at D. We make section somewhere between C and D, right? Yeah, to find the internal force. Yeah, so that the internal force is uniformly distributed lah. When it is far from the section is far from the application of the external force. All right. All right. So anyway, our level we assume it to be uniformly distributed lah. Okay, that's it. All right. Our level, advanced level will consider the section near to the application of the force, and not our level, advanced level. Yeah. All right. So our level is just that you get the internal force, right, and then by the area. That's it. Okay. Yeah. Right, so we have two types of normal stress. Yeah, we have two types of normal stress. Okay, so when you calculate normal stress, let's say you calculate normal stress, you get what? Let's say 10 megapascal. Okay, so if you leave your answer like this, okay, because it's positive, right? Because it's positive. So positive means that it is tension. It is in tension. Yeah. Okay, it depends on the internal force. The internal force can be tension, it can be compression, right? Normal stress, we have either tension or compression. It depends on the internal force. Right. Yeah. So if you give your answer as this, okay, so because it's positive, right? So normally we don't put positive here, don't plus here, right? To represent positive, right? Yeah. So if you give your answer as this, we assume that it is tension lah. Okay. Yeah. Okay. So if the internal force is compression, and you calculate the normal stress, and you give your answer like this, okay, the answer is compression, and then you give your answer like this. So it's considered as part of the answer. It's part of the answer. You must, okay, show whether it is tension or compression by, okay, if the tension, okay, if the tension you can give like this, no problem, because for positive is tension. For compression, you have to put minus here. The compression, yeah, you have to put minus. Oh, well, okay, okay. You have to put minus, okay, minus 10 megapascal. Okay, or you can put it as 10 megapascal. You put C to represent compression. Okay, right. This is very important. Yeah, normal stress, we have either tension or compression. You must state whether the normal stress is tension or compression. Right. For tension, okay, if the answer is tension, you can leave your answer as this, no problem, because for positive is we use a positive sign for tension. Right. Yeah. So if it's tension, you give your answer as equal 10, like okay, no problem, you can accept lah. It is as tension, or you can put T also if you want for tension. Okay, but for compression, for compression, you just put 10 megapascal, no sign, negative sign, or no C, and then it is part of the answer. Okay, yeah. Right. Okay. So far, okay, that's the formula, right, to calculate normal stress. Yeah, show you later lah. Okay, how do we know that the structure can hold the load or not, right? Whether it is it breaks, what will happen to the structure? We will know that based on the stress value. But first, we need to know how to calculate stress. Okay. Okay, if you look for this structure here, okay. So P over A, sigma equal to P over A is for actually loaded members. If you look at here, there is no member under actual load. Okay, there's no member under actual load. Right, this is under transverse load. So later we will calculate the stress due to transverse load later on. Okay, ABC also is not under actual load. Yeah, right. So to determine the strength of this structure, or the size of every member here, later, okay, when we do transverse load, okay, so for this, we cannot use that P over A lah, right, for this structure here. Okay, let's look at next one here. Right. Okay, now we have what? We have G, F, E, okay, and then we have this member here, right? And then we have BD, right? Yeah, BD, and then we have these F, H, B, A, B, C, and so on, right? Okay, now which member is under axial load? Tengku Balkesh.
Yes, Doctor.
Which member? Which
FB,
F?
FB and BD.
FB and BD, yes, good. So we can use to determine the size of this member here, FB and or BD, we can use sigma equal P over A. Right, because it is under axial load. Right, it is under axial load. Now, if I want you to calculate the stress in BD, if I want you to calculate stress in BD, so we need the internal force in BD lah. That's why we calculate all this. Yeah, statics. You have done statics, right? Yeah, this is FBD or FDB, right? Okay, so if you sketch, so this is force in BD or DB lah, 2.6 kilonewton, yeah. So it is in this direction lah, shown here, right? Yeah? Based on this free body diagram, we get FBD positive, right? So means that it is in the correct direction lah. So now, if you want to sketch the free body diagram for BD, right, for BD, yeah, for this. Okay, for BD, right? So you have this force here, FDB in this direction, okay? So it must be opposite here, right? FDB of FBD is same, right? Okay, yeah, must be opposite, Okay, this is in this direction, and then for BD is opposite, right? And then we have over here, right? The other side is the reaction, right? Okay, FBD. Okay, now for BD, we can calculate the stress, the normal stress in just mixed section lah. Right, yeah, the mixed section, okay, so you find the internal force. Okay, so this is FBD, right, which is 2.6, right, kilonewton. Okay, so we have the normal internal force in the material in that direction, right? Okay, this is the internal force. Let's put as P lah, PBD, the internal force. This is what we need to input it in the formula. This value here. It's not this. By right, it's not this lah, right? This is external, but the internal depends on external lah, right? But if you want to input the value in the formula, we need the internal force, right? So in this case here, the internal force is equal to 2.6 lah, right? That's why we do internal loadings first, yeah? Understand what is the internal force, internal load. Okay, so under axial load, okay, there's no shear at the cross section. There is no, yeah, we have discussed this, right? Yeah, for member under axial load, yeah, BD is under axial load, right? So if you make cross section, at the cross section we only have normal internal force, right? There's no shear force, right, on that section. There's no bending moment, right? Yeah, so for member under axial load, okay, at the cross section, not other section, at the cross section, we have only normal internal force, right? Yeah. Okay. So if I want to calculate, what is the stress in BD, I need to know the cross section lah. What is the cross section? Is it circular? Is it square? Or is it rectangular? Okay. Okay. Let's say BD. BD is the cross section is, let's say BD. The cross section is circular. Circular means that we need diameter lah. Okay, let's say the diameter is 10 mm lah. Okay, let's say the diameter is 10 mm. Okay, yeah. So how do I find the normal stress in BD? Right, so I can calculate the normal stress in BD. The normal stress in BD, okay. So we have the formula P over A, right? Okay, so the internal force is 2.6 kilonewton. Yeah, let's change it to Newton. Yeah, unit. Be careful with the units. 2.6 times 10 power of 3, right? In Newton divided by area. Right, the area. Yeah, okay, it is circular, diameter 10 mm. Okay, so how do I find the area? Jimmy, how do I find the area? Are you here, Jimmy? Jimmy tak ada? Okay, Haris. How do I find the Haris, Daniel?
To find the area, must use length and
What?
width. Product of length and width.
Is it? So the cross section is circular. I give you diameter here.
Oh, circular pi r squared.
So what? Okay, pi divided by area. So pi r square. Okay, pi. What's my r? What's my r? What's the value for r to input? What's my r?
5 mm.
5 mm, right? 5 mm. Okay, let's use meter lah. Okay. How to convert that 5 mm to meter? How do I convert it? How do I convert that to meter? So I want to use Newton. This, okay, the force in Newton. Unit, yeah. Don't play with the units, okay? Mass
0.005 meter, is it?
Okay, 0.005 meter, right? Square, right? Pi r square, so you get meter square lah. Okay. So what's the value? Do you have you have calculator in front of you? Ada, Haris?
Ada sir, kejap.
What's the value? Okay, cuba kira. Okay, what's the value?
.1 kilonewton per meter square.
3.1? What? Kilonewton per meter square?
It's quite big.
Yeah, of course. For metal, yes.
33104 228.16 Newton per meter square.
You just press ENG.
What?
You have the calculator in front of you, calculator, right? Scientific calculator kan? You just press ENG.
ENG.
Ada? Tak pernah guna. You tak pernah guna ENG. Tak ada. We don't have course how to use calculator. Okay, press click ENG on your calculator.
33.104 times 10 to the power of 6.
Yeah. If you click ENG, you this 10 power 6, right? Okay. Right?
Newton per meter
Okay, we
square.
take this one, let's say one decimal point lah, 33.1 times 10 power 6, okay? Newton per meter square, right?
Yep.
Okay. So it is what? 33.1 mega Pascal, correct?
Correct.
Betul kan? 33.1 mega Pascal, right? Newton per meter square is Pascal, right? Okay, times 10 power 6 is mega, right? Okay, that's the stress lah. Okay, but do you think that this is complete now? The answer, if I want you to find the normal stress in BD, is it complete? The answer, it's not complete. It is not complete. Okay, as I said just now. Okay, normal stress. Okay, normal stress, we have either tension or compression, right? So if you give your answer like this, okay, because normally we don't put plus sign, right, for positive, right? So if we don't put any sign here, we assume it to be positive lah. Positive is for tension. Positive is for tension. Is it tension? Notice, is it tension or compression? Based on the internal force. Based on the internal force. Is it tension or compression?
It's compression.
It's compression because the arrow is towards the cross section, right? Yeah. It depends on the external. All depends on external. All right. Okay. So the internal force is going in. Yeah. So it's compression. So if you give your answer like this, so it's just part of the answer only. Okay. Or we can say it's not just part, it's wrong. It's wrong. Because it's compressive. You give your answer like this means that it is tension. We need normal stress. We need to mention whether it is tension or compression. All right, because based on the stress value later on, I will show you how do we determine whether BD can hold this weight of this engine or not. We will know later. All right, yeah. The weight of the engine is the mass of the engine is 125 kilogram, right? Yeah, the stress, okay. The stress in BD is 33.1. Okay, 33.1, right? So how do I know based on that 33.1? Okay, this member, based on this 10 mm lah. Based on this 10 mm, I know it can hold this without break. Based on the stress value later. But first we need to know how to calculate stress. Okay, so BD is uncompressive. You cannot leave your answer like this. Right, if you leave your answer like this, it is tension. So you have to put what? You have to put minus. Okay, or you can put C lah. As long as you mention it is compressive. Because what? Some material, the strength in tension and compression different strength. Very strong in compression, but very weak in tension. Okay, some material same tension, compression, same strength. Okay, yeah. So we need to know whether it is tension or compression. Okay, if it's compression, then put C. Right. If it's tension, I can leave your answer like this just now. Right. Okay. Tension okay, but compression, be careful lah. Right. We need to mention whether either it is tension or compression. Okay. Right. So how to know whether BD can support the weight of the mass of the engine? Later lah. First we calculate the stress. Okay. Right. And then how do we determine normal stress in? So we can use also P over A for FB. Because FB is under axial force. Right. Yeah. Different dimension, right? Here different cross section, right? Different size. Right. So based on this figure, right? Okay, what do you expect? The normal stress is section FH and section BH. Which one is higher? Which one do you think is higher stress? Yeah, Aiman. Okay, FB, yeah. Aiman.
Yes, sir.
Okay, right. Aiman.
Yes.
Right now, so FB is under axial load. Okay, we can use P over A. We can use P over A formula to calculate the stress in this member here. But the cross section is not the same. You know, the cross section for FH is smaller as compared to the cross section for HB, right? So, okay, which section do you think that the stress is higher? FH or HB? Which section, which part of this member here, the stress is higher? FH or HB? Is it the same internal force? The internal force in FH and the internal force in HB, is it the same? Is it the same?
FH and
Is it the same? The internal force, when we make section, FH, and then when we make section HB, do you think that the internal force same value? Is it the same or different? Internal force.
it's different.
Okay, if you look at okay, now look at FB, right? Okay. So I put okay, the free body diagram is this direction, all right? And we found that it is positive, that means that it is correct lah in this direction, right? Now, if we sketch the free body diagram for FB, yeah. Okay, so we have FB here in that direction, right? Where we transfer it to FB, it must be here, same point there, must be opposite, right?
Yes.
B, right? Okay, FB, yeah. Okay, so at B, we have also support here, right? So we have opposite lah. B. Okay, yeah. Okay, so if I make section in between FH and FB, HB, the internal force, is it equal or is it different?
It's equal.
It's equal. Right, you make section here. Okay, the internal force in FH is equal to FB here. FB, right? If we make section here, okay, the internal force here also same as FFB. FB on the other side, same lah. Same. Unless in between here, H here, you have another force. That's different. Okay, at H you have another, let's say lah, what, 5 kilonewton. Then it will be different. Alright, yeah. Let's say at H here you have another external force. Let's say lah. Right. Then the internal force in FH and the internal force in FB will be different. Okay, but now there's no applied force in between F and B, right? Yeah, there's no external force applied. Okay, yeah. So the internal force in FH, okay, and the internal force in HB will be the same. Okay, my question just now, Aiman, which one do you think the stress is higher? Which section? FH or HB? It's higher.
FH.
FH, right? Because the area is smaller, right?
Yeah.
Okay, if the stress is too high, in which the material cannot hold, we will find that stress later on, okay? FH will break first. Right, FH will break first. Okay, yeah, because the stress is higher. Right, we will know that later. What's the maximum stress that material can hold later on? Okay, yeah, but first we need to know how to calculate stress. Right, yeah. Okay, for this member here cannot okay, IV first lah. This member is under transverse load, GE. GE is under transverse load. How to determine the stress in GE? The formula is different. If you want to calculate the stress in GE, it's not P over A, different. P over A is for actual load only, for actually loaded members only. Right, yeah? For transverse loaded member, cannot use P over A, different formula. We'll cover that later. Okay, yeah? Right.
Doctor,
Yes.
can I ask you a question?
Yes.
Is this about the unit for area? Because when I used to answer the other question, it given the area in mm squared. So is it gonna change into meter squared or just use that? Because in that
You
question,
can give. No. It's okay. As long as it's okay. Okay, let's say lah. Yeah, okay. Let's see. This one here. Let's say. Okay, let's say, okay. You want to maintain millimeter, no problem. You can maintain. Okay, let's say we solve this. You want to maintain the area in millimeter, no problem. Okay, let's calculate the stress. Okay, let's calculate the stress. Alright, so POA, right? The internal force into point C. You want to use Newton. You want to use Newton, right? Okay. And divide by area. You want to maintain millimeter, no problem. Pi, area millimeter is 5, right? Square, right? Millimeter square. Alright. So you give your answer. Okay, yeah, okay. Apa tadi? Aiman eh? Is Aiman, or is it? Aiman, you asked the question, right? Siapa yang answer? Who asked the question just now? Is it Aiman?
Me doctor.
Siapa ni?
I did.
Aiman eh?
No, sir. I
Siapa
did.
ni? I did eh? I did?
Ah,
Okay, I
I
did.
did.
Okay, I did.
okay.
Okay, right. Okay. Can you calculate this? Do you have your calculator in front of you?
Yes, doctor, but I don't. Pi.
2.6, okay. Exponent 3. You need, okay. One more thing, yeah. You need to know how to use the calculator, okay. There's no course on how to use the calculator, eh? Okay. Betul, yes. Because when you use the calculator, there is a shortcut way to get the answer, and then there's another. Okay, so use the shortcut way. Use memory plus, use memory minus, whatever lah. Okay, use bracket, whatever. All right, yeah, on the calculator, right? Yeah. Okay. Like this, right? Okay. You click, okay, 2.6 exp. You click exp. Yeah, you have your calculator exp. What? Or times something. Okay. 3, right? Exponential 3, right? Divide pi, divide 5 square. Okay. You have to use your calculator. Okay, and then you must use it very fast. Okay. If you take time using calculator, so you lost. Okay. I'm afraid that you cannot solve it within what? 30 minutes, yeah? All right? During the test, okay. So you need to know how to use the calculator. All right, yeah? Okay, I did.
Yes, sir.
Mana nama your name ni? I did eh?
Nik
What is your
Muhammad
full name?
Aidil.
Muhammad.
Nik Muhammad Aidil.
Oh, ni. Oh, Aidil eh? Okay,
Aha.
I say Aidil. Okay, Aidil. Alright, okay, Aidil.
Yes, sir.
Boleh? Can you
boleh.
use the calculator? Okay, berapa dapat? What's the value?
3.31.
2.6. Okay, 3.31.
31. Is it?
33.1. 3.31.
Yes. 3.31 Newton millimeter square.
3.31 get.
Newton over millimeter square.
Macam tak kena je ni.
Hah?
Newton. Macam tak kena. Macam tak sama dengan jawapan tadi. Not the same as this answer. Newton per
Oh,
millimeter square.
doctor. I thought it 10 square. It's 10 cube.
No. Thank you. Yes, thank you.
Oh, if 10 cube, 33.1.
Okay, that's okay.
Okay.
Right. So it's 33.1 Newton per millimeter square. Put C. You can give your answer like this. No problem. Yes. It's correct. Because 1 Newton per millimeter square, okay, 1 Newton per millimeter square is equal, okay, 1 Newton, okay, 1 Newton. How do you convert millimeter square to meter square? Aidil. Aidil, how do you convert millimeter square to meter square? Times 10 to the power of?
10 power of
1 millimeter square equal what meter square? Ini belajar masa fisik. Anyway, okay, use whatever knowledge you have lah during your secondary school, okay? During your physics class, whatever lah. Units very important, yeah. Don't play with units. I have videos on units, the importance of units. Units, okay. Nanti ada masa I'll show you the video lah. It involve nyawa tau. Yeah, because of units. Okay, I'll show you the video later on lah if I have ada masa lah. Okay, if I have time, I'll show the video. It's the importance of units. Okay. All right. So timestamp what? It is.
-3.
No, -3.
Oh, square. Square. -6.
Square. Okay, -6. So it is equal
Okay.
1 times 10 power 6, right? Yeah, Newton per meter square. So it is equal to 1 megapascal. Right, so 33.1 Newton per meter square is also equal to 33.1 megapascal. So if you want to give your answer for SDs, no problem. We accept it, no problem. As long as it's correct. As long as it's correct unit. Right. Okay. Yeah, no problem. You can give your answer like this. Newton per, but it must be correct unit. Okay. But if you give your answer as Newton per meter square, 33.1 Newton per meter square, no lah. Cannot accept that lah. It's wrong. Okay. Give you answer 3.1 Newton per meter square. Let's say lah. Right, it's wrong. It's not the same. It's not the same. 83.1 Newton per meter square is not the same as this. Okay, yeah, right. So yes, you can give your answer as Newton per meter square. No problem, as long as it's correct.
Okay, thank you.
Right. Okay. Now this. Which member is under action load? This member, right? These two force member is under action load, right? You can calculate lah the stress, Okay. What about this? Which member that we can use P over A to calculate the stress? Lim Lee Heng.
Yes, sir.
Which member? Which member that we can calculate the normal stress? Then we can use the formula P over A. Which member? Which member?
I think IJ.
IJ, yes. IJ is under action load, yes. Ada lagi? We have other member.
HF.
HF. Okay, HF. HF is the two force member, right? Is it a two force member, HF? Is it a two force member, HF?
Oh, yes.
Yes, that's why we sketch like this, right? FH, right? Because FH is two force member. The reaction is in direction of FH. But the question now, is it under action load? It is a two force member, yes. But is it under action load? Okay, now, how do you know whether it is under action load or not? Okay, okay, let's sketch FH. Okay, let's sketch FH, free body diagram FH. Like this, right? So we have FH in this direction, right? Yeah. Do we get positive? Is it FH when we sketch the free body diagram in this direction? FH, what do we get? FH positive or negative? FH. Okay, we get positive, right? You get positive, right? Yeah, positive. Okay. Okay, positive. Right. So is this correct direction lah? Is it correct direction, right? So we transfer to for this part here, FH. So it must be opposite, right? Okay, and then the other side lah. Okay, how do we know whether this it is in action load or not? Okay, you just make section. All right, you make section. So we have this. F, H. Okay, at the cross section here, Okay, Lim, do we have this normal internal force? Lim Lee Heng,
Yes, sir.
do we have that normal internal force, FFH? So that it is in equilibrium to this? Must be in
Yeah.
equilibrium.
Mm.
FFH is the internal force, yeah? This is external, this is external. This is internal, this is the internal force in the material. Then we make
Okay.
section here, cross section here, right?
Yeah.
Okay, now is it equilibrium? Do you think that it is in equilibrium?
Supposed to be.
We have distance here, here, and here we have distance, you know. So it means that we have moment.
Oh.
It's not a line. It is not a line. It is not a line. If it is a line, then the moment will be zero. But it is not a line. Here and here, it's offset, right?
Yeah.
So we have moment. Okay, we have moment, yeah. So this FH is not under action load. It involves bending. It involves bending. Transverse load. Later on lah. Okay, yeah. Okay. So FH, even though it's a two force member, but it is not under action load. Okay, yeah. Okay, IG, yes. BC, BC is under action load. So we can use P over A to determine the normal stress. Right, yeah. Okay, if you look at here, if I want you to calculate the normal stress in IJ, okay, you need to find the internal force in IJ, right? Okay, if you know the area, so that internal force divided by area, you get stress, right? Okay, if you look at more work is on to find the forces. To find the stress is easy, right? You know the normal, you know the internal force, you divide by area, you get normal stress. That's it. But more work is on to find the forces. Can see more work is on statics. Right? Knowledge of statics is really neat in mechanics of solids. More work is on statics. Once you get the internal force, okay, not this, this we have bending, right? Okay, in IJ, let's say, once you get the normal force, the internal force in IJ divided by the area, area is not solid one lah. Area you learn area to calculate area during your primary school, right? Area, right? You calculate, you learn how to calculate area primary school, right? You're secondary, lim primary, right? Calculate area of mathematics, right?
Yes, sir.
Betul kan? You learn how to calculate area during your primary school, kan? Betul. Area of circle, area of triangle, right? Okay. So use lah the knowledge how to calculate the area. Use it here. All right. So more work, if you look at here, is to find the forces, the inner force. More work is on statics. To find stress, you just divide the internal force divide by area. Then you get stress. But how do you know that that only in solid lah? How do you know that it can hold? Right, yeah. So how do you know that okay the weight, the mass of the soil is 500 kilogram? How do you know that this can hold the mass of this soil here? With the size of IJ, right? With the material that select, correct material that you select, you know that okay, yeah, you can guarantee that IJ will never fail. That's what we're going to do in solid one. Okay, yeah. But more work is on to find these forces. All right, yeah. So that's on stress, lah. Right, yeah. I'll show you later, lah. Okay, how do you know that with the stress value, you will know that the structure can hold the load, okay, without failure, without breaking. Or other things can happen lah. Not just breaking, not just break. Other things also can happen. Right? Permanently deformed. That's we'll cover that in solid later on. I'll show you. Okay, ada soalan? Any question so far? Okay, any question? All right. Okay. All right. Okay, that's all for today. I hope you faham, ya. Okay, our lecture today. So Excel is okay. So far, just one formula that you need to memorize. A very short formula lah. Right? Sigma is equal to P over A. Yeah. All right. Okay. So we stop now and see you next week. All right. Thank you.